all of Chapter 2 except for one section. So we'll finish that this morning, and then we'll cover Chapter 3 and Chapter 4. There's an awful lot of material to talk about today, so just stay with me if you would, and if you have questions along the way, we'll take them. Yes, ma'am.
Would you be kind enough, for me, I'm using a different book. When you say Chapter 3, would you say the title of it so I can locate it in my book?
Yes, ma'am. Chapter 3 is Electricity, Components, and Circuits. And it begins on page 3-1. You have an old manual?
No, I just have a different one than y'all have. It's a brand new one, but it's not your type, your one. Different.
Oh.
But I find everything you've talked about in here, just in a different place.
I'm not surprised. Yeah, electricity, components, and circuits is Chapter 3, and propagation, antennas, and feed lines is Chapter 4. Before we finish the last section of Chapter 2, I want to go back and talk about something very briefly that we really didn't have time to do last time, but it's very important. If you look back on page, on page 2-3 of your book, and I'm looking at figure 2-2. We talked about last week signals and waves. We talked about frequency, we talked about wavelength. There's a relationship here that is very commonly used that's important for purposes of talking about signals that vary in frequency or single tone frequencies. If you look at the top of page of that figure 2-2, you will see essentially this diagram. Okay? And if we remind ourselves of what that is, this is the variation in amplitude of a signal over time. If we consider that a waveform at any frequency, we're not worried about what this is. It starts at an amplitude of 0. As time passes, it increases to some positive maximum, and this has to be alternating current, right? Because all radio waves are alternating current waves. It increases to a positive maximum. It begins to decline. It passes 0 again. It decreases to a negative maximum and returns to 0 again. And what did we call this? Now what is if a cycle? Right. Okay. Now remember, this is time and not distance. Everybody okay with that? Yeah. So punch the clock on, the signal starts, it gets positive, returns to 0, goes negative, returns to 0. Now if we were to look at this in terms of a circle, those of you who have memory of basic math will remember that the circumference of a circle is equal to 2 times pi times r. And that's really pi times diameter. Okay? And this is a mathematical truism that the ratio of the circumference of a circle to the diameter is constant. And that constant is pi, which is 3.1416 approximately. Okay? Now, if we were to look at this waveform in time, we could also display this in terms of a circle. If we call this 0 degrees and 90 degrees and 180 and 270, and we relate this behavior to a movement around the circle, what is this point right here? What fraction of a wave of a cycle? 180. It's half, right? Well, if we were looking at it this, where would this point here? 180. Okay. What is this? 90. And this is 270. So if we were to talk about the relationship of the waveform in terms of a circular pattern, this would be 0 if a full circle is 2 pi. And the reason we know that is that if we were to say that this number is 1 unit, whatever the 1 foot, 1 mile, 1 inch, whatever, the circumference would be 2 pi times 1. Okay? So now we know that we can say that we have a circle that is 360 degrees in angular measure, but we could also express it in terms of fractions of pi. Okay? So if we know that there are 2 pi, this is called radians, in a full circle, when we get to a half of the cycle completed, that's a half wave. And where are we on the circle? 180. 180. Well, how many pi's is that? 1. 1 pi. And this would be half a pi. That's called a slice. And this would be 3/2 pi. The reason this is important is because you will see a lot of references to pi in terms of measuring things, particularly with respect to the electrical value of components that we'll talk about that have a relationship to frequency. All I wanted to do was just to show you that in terms of phase, if you were to look at the middle drawing on figure 2-2, you'll see 2 waveforms. They are not in sync. And when they're not the same, we call them out of phase. And the distance between, let's say, if this is the other wave, the waveforms are out of phase by this distance. And if this distance is 1/4 of a wave, and we're right here, that we're pi over 2 displaced, right?
Yes.
So when we talk about the phase of different frequencies, we're talking about where they are displaced in time. Okay? This is just another nomenclature. I'm not sure that you're going to get questions on this on the exam, but you could, and it's important to recognize the concept. Okay? So in terms of circular measurement, in terms of phase, we can refer to these in pi's, and we can refer to these in degrees, and here we refer to portions of a full cycle. Everybody okay with that, just as a general concept?
Yes, sir.
And you don't need to worry about writing all that down. I think this is just something to be aware of. Okay. Let's move on to 2-3, and we've called that radio equipment basics. In terms of the basic station organization, and you'll see this on 2-11, page 2-11, what do we need to, what comprises a basic radio station? And we looked at this in a diagram form, and this is pretty well listed in a bullet point form. We need something to receive an incoming signal. We need something to transmit an outgoing signal. We need an antenna to capture an incoming signal and radiate an outgoing signal. And we need some source of power for the radio. Then in addition to that, you will see a bunch of station accessories, but in terms of fundamental or basic station organization, those are the 4 components that any radio station has. This is the picture that's in the book on there on figure 2-10. The other thing that I'll call your attention to that we talked about is this thing in the middle. And this word right here, transceiver. As I mentioned last week, virtually all of today's radios combine a transmitter and receiver into one box, and it is called a transceiver. That's why you've got the dotted line that encloses the transmitter and receiver. If they're all in the same box and we can't transmit and receive at the same time, we have to have some way to switch the radio from receive mode to transmit mode, or from transmit mode to receive mode. And that's called a TR, or transmit receive switch. This is all done electronically inside the radio. So there's no switch you have to flip outside to change from transmit to receive. A lot of times microphones that have a push to talk switch, when you push the button, you're activating the TR switch, you are silencing the receiver and enabling the transmitter portion. Okay? Need to talk for a minute about some special stations. This will be very important to those of you who get your license and get radios and start talking in terms of local area communications. Those of us in Williamson County who want to talk to other Williamson County stations or those immediately adjacent to Williamson County use a device called a repeater. And a repeater is actually a radio station. This is described at the bottom of page 2-11. But repeaters are automated VHF or UHF frequency stations, generally located on tops of buildings or on tops of hills that have the ability to receive and transmit signals simultaneously. Now that's unlike the radio you have in your hand or your car or your home, which once you turn the transmitter portion on, you can't receive anything. And as long as you have the receiver on, you can't transmit anything. The interesting thing about repeaters is that they can receive and transmit signals simultaneously. And they do that through a device called a duplexer. You can think of a repeater as a relay station. These are not manned. There's no operator at a repeater. It's all automatic. They have the effect of increasing range. Let's say I was in Fairview and I wanted to talk to somebody in College Grove. That's a pretty long haul across Williamson County. If I had a small low-power radio that I could not, if I was in Fairview, I couldn't get the person in College Grove to hear me. But if somehow I can transmit my signal to a repeater location that my radio can see, in terms of the line of sight, or roughly line of sight, and the station in College Grove can also see that point line of sight. Although we can't see each other, we can transmit through the repeater. It is a radio station. It has a transmitter and a receiver and a power supply and an antenna. But the curious thing about this is the duplexer feature and the fact that it can receive and transmit signals simultaneously. They use the same antenna because the difference between the transmit frequency and the receive frequency are pretty small. The reason the duplexer is important is that if I'm transmitting on this frequency and I'm receiving on this frequency and they are so close together, I don't want to interfere. I don't want the transmitter part of the repeater to interfere with the receiver part of the repeater. The duplexer has the effect of providing essentially total isolation between the two frequencies. And that's the primary function of a repeater. Everybody more or less okay with the general function of that? Let's see, make sure I don't get ahead of myself here. This is the typical repeater station. I want to, if y'all can see this in the back, let me show you something here that I think will help, hopefully will help put this in perspective. I'm going to call this the repeater, the RPTR, and it has a receiver section, which I'll call RCVR, and a transmitter section, which I'll call XMTR. Okay? Now I've got radio station over here somewhere. This is station A, and it has a transmitter part of it and a receiver part of it. And I've got another station over here that has the same thing. It has a transmitter and a receiver. So the repeater as a radio station has the same element. I haven't drawn the antennas on here or the power supply, but obviously they both have to have that. So I have 3 stations here. 2 of them are operator stations and 1 is a repeater station. So if I want to talk from radio A to radio B, and I want to talk through the repeater, I've got to transmit on the frequency that the repeater is listening to. Okay? Simultaneously, the repeater transmits on the frequency that this station can receive. So I'm going through a radio output, repeater input, repeater output, radio input. And if you were to reverse the process, that's what you would do. If in this case, the repeater acts as a broadcast facility. It doesn't have any directivity or anything. It just transmits a signal. So the fact that station A can actually receive can actually communicate through the repeater, and so can station B. All I'm doing is using my radio to transmit on one frequency, which is the repeater input, and I'm listening to the output. But as long as I'm transmitting, I can't hear this. In other words, my station can't transmit and receive at the same time. So I push the microphone, I start talking into the microphone, the radio transmits, the repeater hears it, it retransmits it out, and the guy over here can hear me even though we may be 30 or 40 miles apart. And if station B wanted to talk to station A, you just reverse the process. The key here is that there are 2 basic frequencies involved in repeater operation, be it at the radio level or at the repeater level. One is the repeater input frequency, and one is the repeater output frequency. And the difference between those 2 frequencies is called the split, or offset. Now, whatever the offset is here, I've got to have the same pair of frequencies or offset established in the radio. So if I was going to, let's say I was going to talk to Beth in the back, and she's radio A over here, and I'm over here radio B, and we're so far apart distance-wise that if I were to transmit and she was listening on that frequency, she couldn't hear me. So I set my radio to transmit on one frequency and listen on another. She sets hers the same thing, so that now when she talks in her microphone, she's transmitting through the repeater, and I hear it over here. When she stops talking, her radio switches back to receive, and if I want to answer her, I start talking, and now I'm transmitting here to the repeater. It's transmitting out, and the station here hears it. Yes, sir?
Wait, but how would you know what frequency the receiver is working at?
Fantastic question. How do we know? There are a set of conventions that are used for standard offsets or standard splits. They are by convention, and you can set these in radios. So if we know that we are using a particular repeater, VHF or UHF, or depending on which of the receive frequencies and transmit frequencies in the repeater are in use, I know from that how I need to set my receiver and transmit frequencies. And those are, as I say, they're by convention. They're not legally required, but there are directories that list any repeater that's operational will provide you with what its input and output frequency is. So at all the time, your receiver in your radio is listening to what frequency? In the what repeater frequency? The receive or the transmit frequency? Transmit, okay? When I turn the mic on and start talking, I am transmitting on a different frequency, which is the receive frequency of the repeater. So repeaters are integral to county-wide communications, and we have 5 repeaters in Williamson County. Fairview, 2 in Franklin, Brentwood, College Grove. Help me, Gary. We've got Fairview. We've got 2 in Franklin is 3. College Grove and Brentwood is 5. The interesting thing about these are all county-owned and maintained repeaters. If you were to go down the Columbia Highway, I guess, if you were going down to the Justice Complex down here, headed toward McHatcher, and you look to the right, there by Century Court, up on top of the hill, there is a tower, and there is a repeater at that location. If you were going down Franklin Road to Brentwood, and you passed right roughly at the Concord Road intersection, headed north, and you look up to the left, there's a tall hill, and there's a radio tower up there. There's a repeater there. There's another one down near the old incinerator. Is that what they call it? Down south of Franklin. There's a tower and a repeater facility there. There's one in Fairview and one in College Grove. The interesting thing about these is not only are they maintained and operated by the county, they are all linked. So as long as you can talk through one, you can talk through all. It's because of the linkages. I'm not going to get into the technical aspects of that, but the 5 repeaters are all linked. So all I'm worried about in Williamson County is talking to the nearest repeater location. Question?
So repeaters are basically for just for you to like if you have like a low frequency radio to repeat it to somewhere at a farther distance.
That's part of it, but the real function of a repeater is to act as a relay station. It's just an unmanned relay station. And that's all. Is that pretty clear? Other question? Yes, sir.
Just to understand the duplexing part, if radio A and B were both transmitting and they were talking past each other, a third person could actually hear them talking but not hearing each other. Is that correct? Since it's transmitting both at the same time.
Okay, that happens a lot.
Is that what crosstalk?
It's not crosstalk. It's just one signal. The stronger signal will tend, if they are a roughly equal strength, you can't hear either one. They just sort of combine and cancel each other out, so you can't really hear. If one is real strong and the other is real weak, often you can hear the stronger of the two, but you can tell in the background you're hearing some other station trying to talk through the repeater at the same time. But technically, you can't both communicate through a repeater at the same time. If this is in use, it's only in use, one increment at a time. I mentioned this is called a private line, or this is a Motorola, old Motorola designation. PL is a sub-audible tone that you can actually impose on a radio signal that has the effect of locking out or unlocking access to a repeater. In other words, if somebody is trying to talk through this repeater from here, and this repeater has a PL tone, and this transmitter is not configured to transmit that PL tone, it can transmit on the frequency, but it won't activate the repeater. And the purpose of that is, in some cases, repeaters have the same pair of frequencies, and they could be fairly close together geographically. So we don't want somebody over here in this sort of geographic community transmitting on a frequency that would activate the repeater over here. Well, the way we do that is that we put a different PL tone on this repeater and that repeater. It's just, think of it as just an access code. Yes, sir.
Can you help me define when you said a low power radio? What's low power? I mean, 5 watts, 10 watts?
Well, if you're talking about a handheld radio, you're talking about maybe half a watt.
Okay.
Some up to 5 watts.
So is there a range then that would define truly low power radio? Is it 10 watts and less?
Not really. It
Okay.
depends on the geographical distance of the communications. I mean, between point A and point B, half a watt might be fine. Between point A and point C, the lowest power you would need to communicate may be 5 watts. So low power as such doesn't, in terms of VHF and UHF communications through repeaters, doesn't really have a characteristic definition. Station accessories. These are things that you add that are nice but not mandatory. If you want to talk voice, you have to have a microphone, so in a sense that is mandatory. Speaker, an external speaker. Most radios have a built-in speaker. Headphones to listen to when you want to not hear the receiver in the radio. A computer to, in some cases, perform functions on the radio or record information about communications that you're having with somebody else. A Morse code key if you're using Morse code. A TV camera if you're using amateur radio television, which is very, very rare these days. Performance accessories. An antenna tuner, we'll talk about that later. An SWR meter, you don't know what that is yet, but you will. An amplifier, an antenna rotator, filters, software for the computer, and other things. These are just accessories, and there are pictures of those in the book. Thus, there is one thing that is missing on this diagram that we talked about in terms of a basic radio station requirement. Anybody recognize what it is?
Power supply.
Power supply. It is presumed here that the transceiver's power supply is built in. Most radios that are not handheld radios, battery powered, have an external power supply. Yes, sir?
In the book, it's got a power supply.
The book diagram has a power supply. The PowerPoint slide does not. The assumption here, this being a transceiver, that it has the power supply built in. A handheld radio that is battery powered has an internal power supply. Here are a couple of questions from the pool. Everything we just talked about. What type of amateur station simultaneously retransmits a signal to another amateur station on a different channel? Or we don't talk about channels in amateur, we talk about frequencies. So what would it be? Repeater station. It is an amateur radio station. It is operating on an amateur radio frequency, but it is not manned. Now, what could be used in place of a regular speaker to help you copy signals in a noisy environment? Yes, sir. C, a set of headphones. Figure T5. This is the transceiver. Block 1 is the transmitter. Block 3 is the receiver. What is the function of block 2?
B, the transmitter, receiver.
transmit, receive, or TR switch. Everybody okay? This is pretty straightforward. I mean, the questions are not real tricky. Anything so far on this before we switch over to Chapter 3? Okay, if you'll let me pause for just a minute, see if I can get this. Okay, now we're into the what in the world is this topic? Are we generally, everybody generally comfortable with what we talked about so far and without trying to get too much into the nitty-gritty? Let's talk about electricity, one of my favorite subjects. Electricity, in the most general sense of the word, is the flow of electrons through a conductor. And a conductor is something generally metallic that would permit the flow of electrons through it. An insulator, conversely, is something that would not let electrons flow, which would be a piece of plastic, a piece of wood, a piece of Bakelite, PVC, glass. Electrons are negatively charged atomic particles. Atomic or atoms have electrons, protons, and neutrons. When electrons move, it actually produces what is called electric current. The opposite charge of an electron is a proton, or positively charged particle. A conductor allows electrons to move with relative freedom within the material. In terms of radio communications, we use the term electronics generally to represent the concept of controlling the flow of electrons or electric current. Because everything that is that goes on inside a radio has something involving the flow of electrons. That's just a given. So we need to understand how we control the electron flow in order to make the radios do the things that we want them to do. There are three basic components of electricity. And I'm going to, hopefully you all can see this. We'll go through this real quickly. Voltage, current, and resistance. Voltage what it is, we can say one of two things. It is EMF, which we refer to as electromotive force, or potential. Okay? We measure voltage in volts, interestingly enough. We measure, and this would be the symbol V. We measure voltage on a voltmeter. So the device that measures voltage is a voltmeter. And if we are dealing with it mathematically, we refer to volts with the letter E. It refers to voltage in volts is a V if you're measuring it. If you're dealing with it mathematically, we use the letter E. Okay? The second is current. And using the same analogy here, this is really electron flow. It is expressed as amperes or amps. And it is measured, what kind of meter do you think would measure amperage? An ammeter. How about that?
Do you pronounce that ammeter or ammeter?
Yes.
Okay.
Ammeter.
Ammeter.
Ammeter. Not meterized kilometers, you would pronounce kilometers, but this is an ammeter. Ammeter. And mathematically, we refer to current as the letter I. Now the other is resistance. And this is something that opposes current flow. Okay? It's measured in terms of ohms. And that, this would be A, by the way, amps A. Ohms, is expressed with the Greek letter omega, just by convention. Now, what kind of meter would we use to measure resistance? Ohmmeter, okay? And mathematically, we use R as the symbol for that. And that's pretty much what this is talking about here, okay?
Resistance basically like controls how much current.
Yes. Everybody hear the question? What the comment was, resistance basically opposes the flow of current? And the answer was yes. Before we look at this, these things are all related. Well, I guess we can go ahead and talk about this for a minute. This is in your book, and it is on page 3-2. This is figure 3-1. If you look at the visualization of voltage, current, and so forth, if you considered a pump, and this is a pipe with fluid in it, the pressure of the pump would be analogous to what? No, the pressure or the force that produces the flow would be called, in electrical terms, what? Voltage, okay? Here is the pressure gauge, which is the equivalent of what kind of meter? Voltmeter. Here is the flow of fluid through the pipe, and here's a device which is a flow meter, not flowmeter. It is measuring the flow of fluid through the pipe. What's that analogous to? Ammeter. Okay? Here is the analogy in electrical terms. This is a battery with a positive and a negative charge. It stores potential. Here is a conductor. If you measure the voltage between the positive and the negative terminal on the power source or the voltage source, you would read the voltage. The voltage is simply how much electrical charge is in the device compared with the positive terminal and the negative terminal. It's electromotive force. Battery, this is a symbol of a battery. A battery is a voltage source. A generator is a voltage source. Okay? If you measure, in this case, current flow with the ammeter. Okay? So these things are all related. If you have a circuit, electrical circuit, you've got to have some elements of voltage, current, and resistance in the most simple terms. For current to flow, you've got to have two things: a source of force and a path to flow. It's just like the water flowing through the pipe or the fluid through the pipe or a hose. If you change the voltage, you affect the current. If you change the resistance, you affect the current. If you change the resistance, you can also affect the voltage across the resistor or through the resistor. Ohm's law is the relationship that combines voltage, current, and resistance. This is depicted in your book, page 3-4 at the top of the page. This is a depiction of the simple. This is something you have got to commit to memory. There will be questions on the exam that deal with this relationship. The reason this is described the way it is visually is that it expresses the mathematical relationship between the three components. If I knew what the voltage and the resistance was in a circuit, and I wanted to know what the current was, in this case, what I don't know is the current. If I were to cover up this, I could determine the current by dividing the voltage by the resistance. If I knew everything but the resistance, I could cover that up and I could find it by dividing the voltage by the current. Okay? If I didn't know what the voltage was, but I knew how much current was flowing through the circuit and what the resistance was, I would multiply the two together. So this E equals IR relationship is fundamental. It is Ohm's law. And the fact that volt, amp, and ohm all are named after people. Friedrich Ohm is the person attributed to the source of Ohm's law. Okay? V for volts we measured, but we express it mathematically as E. Amps, we describe it in terms of 4A or 4 amps. It's expressed mathematically as I. And resistance we measure in ohms. So if I was to say I have a 20 ohm resistor, I would write it as 20 omega. But it refers mathematically as R. Okay on that? Let's talk about circuits for a minute. Circuit is just the path that represents the path or where electrons flow from one point to another point. The pump, the hose, and the flow of water analogy that we talked about. There are two basic types of electric circuits or electronic circuits. This is in your book. This is at the bottom of page 3-2 at the top. This is called a series circuit. And in this case, we have a source of voltage and we have a conductor, but we have three resistances or three resistors in the circuit. And each one of these, they could be the same resistance, they could be different. But what this tells you is that the current in a series circuit flows ultimately through only one path. Okay? This is the other figure on that same page. This is a parallel circuit. And in this case, because I've essentially got multiple paths for the current to flow, I've got a voltage from here to here, don't I? So there is a current path through R1. I've also got the same voltage across R2 and R3. So I've got current flowing from this way, I've got current flowing this way, and I've got current flowing through R3. Current is everywhere. That's a parallel circuit, and the other was a series circuit. Let's talk about resistance for a minute. As we talked about, what resistance represents is the restriction or the impediment or the obstacle of the flow of current. And it is determined by the physical composition of the material involved. We talked about the difference between an insulator would be equivalent to a resistor. a conductor of any kind usually has some amount of resistance, even though it's pure metal. But generally speaking, conductors are metallic, insulators are non-metallic. Now, if we want to, just having current flowing through a circuit, just to have it there doesn't do anything for us. So in terms of letting electron flow or current produce a useful output, we have to create energy. And energy, in fact, is created during the flow of electric current. Electrons moving through a conductor or a circuit actually do work, and there is power involved. So think of power as the result of electron flow to do something useful. And we express power in watts. So if I had another column over here, and I call this power, it would be work done, or energy, power is expressed in watts. It's measured with what kind of meter? Yes, a watt meter, right? A watt-meter. And mathematically is expressed by the letter P. What have I done? Is everybody generally okay with this concept? We've got three fundamental parts of electronics and the result of useful application of electronics. In terms of how you would determine this, if we say power is equal to voltage times current, but if you think of Ohm's law, if we didn't know the voltage, but we knew the current and the resistance, we could say that E equals IR, doesn't it? So if we were to replace one of the I's, if we were to replace one I with an IR, we would get I squared R. If we didn't know the current, but we knew the resistance, we know that current would be E over R, or E times R, or E squared over R. This is just the mathematical relationship, the three forms of the power relationship. There will be a question probably on the exam pool about that. There are some in there, and you will see them probably on your exam.
I can write that down. It's right here. Oh, okay.
Two types of current. Current flows in one direction only. It's called direct current. That would be what is produced out of a battery. A battery does not produce alternating current. And by alternating current, it has a waveform. It starts in one direction, increases to an amplitude, decreases to a negative amplitude, and returns to zero. And it produces a waveform. Now, most devices are powered by direct current, but they convert direct current to alternating current within the devices sometimes. So you can't say that everything that goes on inside a device or a radio is direct current. It's not. But the power source for most radios is direct current. It produces 12 volts DC. 12 volts means that's the potential or the voltage in the device, and it produces DC, or direct current. If current flows alternately in one direction and then another, it's called alternating current, or AC. Your household, if you plug something in an outlet at home, you're tapping 60 hertz alternating current, and it's at a voltage of about 110 to 120 volts AC. When you plug a lamp in the wall, You're actually creating a circuit. The voltage at the receptacle is connected in a circuit that represents the wire. It goes through the bulb in the lamp and back to the other pin in the plug that goes in the wall. So you're actually causing current to flow through the light bulb. And it's a series circuit. Light bulbs are represented in terms of watts. That's the amount of power consumed in the bulb. It's the same concept we've talked about here. Okay, let me see if I can. Everybody okay with the power formula? Okay, whoops, I told you the answer before I asked the question. What term describes the number of times per second that an alternating current reverses direction? If you don't know this by now, I'm going to ask you to leave the room. Alternating current. What do we call the number of times per second? The pulse rate?
No.
Speed? Wavelength? Frequency? Frequency. How many times a second does the direction change? Electrical current is measured in which of the following units? Yes, sir. Electrical current is measured in what unit? Yes, sir.
D, amperes.
Amperes. Okay? Current is amperes. Volts represent voltage. Everybody okay on that? Power measured in which of the following units?
B, watts.
Watts. Okay, everybody all right with that? That's not too bad. If you get some of these, it's a slam dunk. Which is the name for the flow of electrons in an electric circuit? Capacitance, what's that? Resistance, voltage, or current?
Current.
Somebody else. Beth?
Current.
Current. What is the name for current that flows only in one direction? Direct current. What is the electrical term for an electromotive force that causes electrons to flow? Voltage. Which of the following is a good electrical conductor?
Copper.
Why are the others not good conductor?
They're good insulators.
They're not generally not metallic. Let's see.
Glass.
Everybody think glass? Right. The other three are metallic in nature. Okay, let's see what we got here. 09. What is the name for a current that reverses direction on a regular basis?
Alternating current.
Which term describes the rate at which electrical energy is used? The rate at which or power is produced. If you think about the consumption or the use of energy, it's done to do work, and work represents power. So if you see this, energy generally is referring to power. Okay, 11. What's the basic unit of electromotive force, EMF? Okay. What is the formula used to calculate electrical power in a DC circuit? We just talked about the circular diagram. Power in a DC circuit equals volts times amps.
Yes.
Power equals volts divided by amps. Volts minus amps. Volts plus amps. What do you think?
A.
Right. Let's see, DO1. Which formula is used to calculate current in a circuit? remember your circle diagram. Current equals voltage times resistance, voltage divided by resistance, voltage added to resistance, voltage minus resistance. Anytime you deal with the relationship between these three elements, there's nothing added or subtracted involved. So you can just knock those two out right away. What?
B.
You think B? How about that? Everybody all right with that relationship? As I say, you've got to memorize that Ohm's law diagram, because I'll guarantee you there's going to be a question or two on the test about that. Which instrument would you use to measure electrical potential or electromotive force? That's this, isn't it? So the answer would be a voltmeter. Voltmeter. Okay, this is.
We have to make everything.
I know. I'm just teasing. What is the correct way to connect a voltmeter to a circuit? Think about the diagram you saw.
Parallel.
Series.
Oh, why parallel?
Because I'm measuring, I'm not including it
You got it?
in the,
You're not measuring the flow of current. You're measuring the potential or the force that causes the current to flow.
it's not a part of the circuit. It's
Right.
measuring.
It's across the source instead of in line. It's not in the circuit, it's across the circuit. Everybody all right with that?
Yeah.
Okay, we're going to skip that one. Which of the following precautions should be taken when measuring circuit resistance with an ohm meter? Think about this for just a second. You've got an electrical device that is plugged into the wall and turned on, and you want to measure the resistance somewhere inside the device. What, from a safety point of view, would you want to be sure you did before you measured the resistance?
B.
Plus to plus, minus to minus.
Now think about it in a minute.
B. I think you'd always want it grounded. B.
Yeah, grounded.
Somebody says, how many think C is right?
I'm going C.
Okay, got some C's. What about B? Got some B's. Anybody for A or D? Well, the answer is this.
How do you measure it if it's not power?
Resistance is an inherent quality of the device. Resistance doesn't change when current flows through it. Okay? It is a fixed quantity, and it is determined by the composition of the material that represents the resistor. Okay? Yeah.
So how do you know which compositions are better resistors than others?
You read the book,
Um,
not that book.
oh,
If you want, there are, and we'll talk about this later as we get into components, but there are different types of resistors made with different types of material. Depending on the shape and the size and the composition, some will have more resistance than others. Some will have the capacity of dissipating more power than others. It's strictly a function of the design and the composition of the component itself. How are we doing on this so far? Any questions?
If you were to have the power on and use an ohm meter, would it hurt the ohm meter?
Possibly. Why? And think about that for a minute. If you've got a resistor and a battery, so you've got, what do we have here? Parallel or a series circuit? Series circuit. It's got one path. Now let's just say this is a 1,000 volt battery. Okay. What we know is that all of the voltage here equals all of the voltage across here. In other words, I can't have the voltage, if I've got 20 volts, that represents the difference between the charge on the positive side and the charge on the negative side. I've got a 20-volt battery.